Hello everybody to today's video. In today's video, I'm going to tell you a little bit about Quarkus and building native images. So what exactly are native images? If you remember the dark ages, so 80s and 90s, for example, if you build a code, you usually use the so-called ahead-of-time compiler. So for example, C++ is a typical ahead-of-time compiler. An ahead-of-time compiler compiles your code into machine code directly, because machine code is the only thing that your computer can understand at the end. This has some advantages, but also some drawbacks, being, for example, that your code can only run on a specific machine. So ahead-of-time compiler code runs on an Intel machine or runs on an ARM machine, but not both. So at the end of the 90s, with the rise of Java, Java introduced the so-called JIT compiler. And the JIT compiler works differently. So if you compile your Java code, it will be translated in some kind of intermediate format, not machine code. And then if you start your application, the JIT compiler will just in time compile your code into machine code during runtime. This again has advantages and disadvantages. The advantage is that your code is now able to run on multiple machines. So because you only have this intermediate format and you have to use a JVM, it can run on an Intel machine. It can run on an ARM machine. It is even possible to run on a mobile phone, for example. The drawback, however, is that from a memory perspective, this uses a lot of memory resources. And startup times are much slower than with a ahead-of-time compiler. So now, fast forwarding to nowadays, 2022, at least as a recording of this video, we now have the requirement that we have applications that can start fast and use less memory. And this is where GraalVM native images in Quarkus kick in, because now they kind of take a step back and it is now possible again to build ahead of time code with Java. And this is basically what's going on here. However, with all the benefits here, there's also another drawback. The JIT compiler, performance-wise, CPU-wise, is very efficient. So the ahead-of-time compiler has to predict ahead of time how to optimize the code. So it has to do some prediction in which way will the code run. The JIT compiler has the advantage that it can do this decision during runtime, which can lead to more efficient code from a CPU perspective during runtime. But for memory and for startup times, the ahead-of-time compiler is usually more efficient. But just to keep that in mind, that this is something we want for things like cloud-native applications. So now let's take a look into the code. We have a standard application, a standard Spring application that is here. You can find it on my GitHub account. That's a so-called person service. Basically, standard Spring application with some kind of REST interface, access to the database, and that's basically it. As always, you can just run this application. It will compile the application and it should just work right away. So we can go here, localhost 2800, and it works. What we can, of course, also do is to have this running in a Docker container. This is already prepared. So here inside my source deploy Docker, I just say stack up, and it will create a Docker container together with a base image and a JVM. So everything started nice. So we have an application and a Postgres database, and it's of course the same application here. So find the first name, for example, find all, and stuff like this. If we take a look, however, on the resource consumption, we see that this takes a lot of memory. It takes about 200 to 300 megabytes of RAM here. which is not so nice. And this is already the optimized format using the so-called OpenJ9 JVM. If you use a hotspot JVM, it will use even more resources. So not so nice. And also, if you take a look at the startup time, we would see that it will start up in a couple of seconds. Okay. But of course, the benefit here is that it could run on multiple machines. We shut down everything, and now in contrast, let's take a look at the Quarkus application. So, first glance, of course, I organized it a little bit this way. You see, it looks pretty similar. So we have the same packages here, whatever the packages mean. I go into details later. And it looks very similar, doesn't it? Yeah. And that's the interesting part. So basically, Quarkus is based on Java EE and the so-called Eclipse microprofile. And it seems that they took a very good look at what Spring currently does and tried to adapt this to the so-called Java EE world. But in contrast to application servers we used in former times, now with microservices. So basically, it's very, very similar. So for example, this is our REST interface here, which does not have Spring's add-get mapping, but instead it has add-get and add-path. But other than that, if you know Spring applications, it's very similar. This will delegate to a logic. The logic will talk to a so-called repository, also like in Spring. The repository will pull the data. We have some kind of mapping here with map struct. And that's mostly it. So if I start my application, it's also an application class like we have in Spring. It will compile the class. It will not build a native image. This is standard Java here. And we can access the application. So looks totally similar to my Spring application. It just has here Quarkus. But other than that, it's similar. We have a finders here. This would do a REST call. We have an health endpoint here. We have a Prometheus endpoint here. And we also have Swagger API documentation here. And the compile process does not take very long because this is running on top of a JVM. So, but it takes 2.7 seconds to start. So now what about the native part, you may ask? Yeah, that's the interesting part now. To get a native image, and the best option is here to get a native image inside a Docker container. You can just tick these two profiles. I have an ARM machine here, so I also tick the native image ARM, and then I say clean package with the profiles checked. And what will happen now, you will see it in the console here. It will do the tests. And it will then start a so-called builder inside Docker. This is not important for building the Docker image, but the build process itself is running inside Docker. This is very nice because otherwise you would have to install GraalVM yourself. And then on my machine, I would get a Mac image. But what we need in Docker is always a Linux image. So instead of installing all this stuff, you can just leverage this technology here. It's hidden in the parent POM at some point in time, and it will then do the build inside Docker. What we already see here, the memory resources we might save during runtime will be consumed during compile. You see, this is what the compiler needs to consume of RAM. It already takes up 1 GB of RAM, and this will rise. This is already very optimized for GraalVM images. GraalVM images during compile time can take up to 6, 7, 8 GB of RAM. And the other downside, it takes a while. So this compile process will take a couple of minutes. In contrast, if we just do the JVM compile. So this is nothing you want to do during the development cycle. This is something you usually want your Jenkins build to do. It's important to stress that you can still develop your software as usual, because you don't need to build a native image. And if you're satisfied, you can either build the native image on your own, like I'm doing this, or you have, your best option is to have some kind of continuous integration pipeline, which will do the longer native image compile. And you see already the memory consumption rises. This, of course, also means that your Docker needs to be configured for this. So in my case, if we go to preferences here, resources, you see my machine has 6 gigabytes of RAM given here. If this would be the standard settings like 2 gigabytes, the build process won't work. It would just crash. But again, Quarkus is already very optimized and it's very fast. So the build process takes about 2 to 3 minutes. And then we should have an image here, which is very good and very fast. So we are already at the so-called inline process, compile now, and it should be finished in a minute. Okay. Takes a little longer than expected. And now it will build the base image, the image in the base image, and now we're done. What happened now is that we have a local build here, so it's also installed inside your local Docker. So now, if I again now in Quarkus do stack up, this will start our native applications. Starting. I hope it will start. So I guess so. And here's our Quarkus application. Looks very similar like all the other things we have seen, right? Okay, but now the difference. If we now take a look here at the memory consumption, you see it's only about 20 megabytes of RAM. You remember the Spring application used 200 to 300 megabytes of RAM. So this is 1/10. Please keep in mind this is under idle conditions. So the application is currently not doing a lot. This is basically bootstrapping the applications and doing nothing. Of course, if you have your application which has crazy requirements like copying huge chunks of data around, I don't know, 50 megabytes, 100 megabytes, of course, you would also see this 50 or 100 megabytes of RAM. This is nothing that Quarkus can do for you. But a basic application after bootstrap will take up to or less than 1/10 of memory. So remember that. Instead of having one Spring application, you can now deploy, from a memory perspective, 10 Quarkus applications. And I think that's a big deal here. And also the startup time is very, very fast. So you see started in, it's less than a second. And this is something we usually want for our cloud native applications. Okay, I'm gonna stop this guy again. We can have a short, deeper dive into our Quarkus applications and maybe some differences we have with Spring. So as I already pointed out, the REST interface looks very similar. We have our logic delegating to repository. We also have a so-called adapter with which we can do a REST call. And this is one of the first differences we have in Quarkus. So usually if we have a Spring application, we use some kind of REST template and we have to build the client ourselves. We have to do something like do a post call or do a get call. And we have to do this programmatically. Here, it's a declarative approach. So what we only need to do to call another application is to define an interface. So this is the so-called callee service adapter. And we can annotate basically the same annotations we have on our service class, so get and path, which are standard JAX-RS applications, to this interface. And then we can just say add inject, add REST client, inject this adapter, and then we can do REST calls, which is pretty nice. Yeah, another similarity Spring is, in Spring we usually have add auto wired, in Quarkus we have add inject, but that's it. So no need anymore to build any REST template clients. That's very nice. On the persistence level, there is again a difference. Quarkus also knows this concept of repositories like Spring Data does, but it's not that nice. So with Spring Data, you usually have these, let's take a look here, persistence, repository. You have this interface class, and you can just say find by first name or find by last name, and it will create the JPL queries for you. In Quarkus, it's a little bit different. You have to do a little bit more. You have this find methods and parameters with stuff that you need to do. It's not that nice, but it basically works the same way. So that's also a difference here. Let's take a short look into the POM file, which is also very important. So one of the major benefits of Quarkus is that they already give you a set of libraries that will work with native images, which is not for which you cannot expect from the beginning, but they just do it. So we have our libraries we need for web application. We have something for monitoring. So for our health endpoint, for Prometheus, we already have OpenAPI, which we can use here. Then, of course, we have Lombok and MapStruct. This is not by Quarkus. We have security stuff. You always see if it's prefixed by Quarkus, it's from them. And we have an Hibernate implementation. Also Flyaway and other stuff. Why is it so important to stress this? Because, again, one of the downsides if we have native images and ahead of time compilers is that every library needs to be adapted for this process. So usually, most of the libraries use things like reflection or proxies. And right from the beginning, these things won't work with an AOT compiler because these are things that are usually things that only work in the JIT compiler. So what the Graal people and the Quarkus people did is to find workarounds and solutions to get this dynamic things like proxies and reflection working with an ahead of time compiler, which is not an easy thing, but they got to work it. The problem is whenever you use a third-party library that's not managed by Quarkus, you can expect it not to work and to crash because every library needs to be adapted. And this is very nice because this is what the Quarkus people already did. So for all the basic requirements like having JPA access, like monitoring and other stuff, the Quarkus ecosystem will give you a library. In contrast, for example, like Spring Native, which I might cover in another video, they just give you some basic libraries, and all third-party libraries you have to bring in on your own, and they either work or they don't work. One more thing, if you have a third-party library, you have to do some things on your own. So, for example, I have this audit JPA listener. And you see, we have an annotation here, which is called register for reflection, which means because this JPA listener gets called via reflection, I just have to tell Quarkus, okay, this uses reflection. Please keep this in mind if you build your native image. But that's it. It's not a lot. And there is another example I'm currently using for using encryption to my database, which is leveraging zipped. You can also have the register for reflection here, but other than just having an annotation, which basically says register this class for reflection, you can also have some kind of list, say this class and this class. But that's it. The whole application, top to bottom, with everything inside there, only needs these two annotations for libraries that are outside, a little bit outside the Quarkus ecosystem. And other than that, it will work. Okay, that's basically it. Thank you so much for joining me today. And if you liked what you saw, I hope we will see each other in the next video.